Hey, have you ever really stopped to wonder how the phone in your hand or the chair you're sitting on actually came to be? I mean, how did they go from just an idea to a real physical thing? Well, it's all thanks to this sort of hidden language, a universal code that designers and engineers use to make imagination real. And today, we're going to learn how to speak it. So let's start with that big fundamental question, right? How does a complex three-dimensional idea that's stuck in one person's head get communicated so perfectly that another person, maybe on the other side of the world, can build it exactly the way it was imagined? And this leads us right to the core challenge here, what we can call the 3D to 2D problem. You see, an idea might feel crystal clear in your mind, but your imagination doesn't really do precise measurements. To build something right, you need an exact, standardized set of instructions. And let's be honest, a quick sketch on a napkin just isn't going to cut it. So what we absolutely need is a system, a way to translate a 3D object onto a 2D surface, like a blueprint or a computer screen, with perfect accuracy. No weird angles, no perspective tricks that fool the eye, and absolutely positively no confusion. Every single detail has to be perfectly clear. And that system, well, it's called orthographic projection. Now, I know, that sounds super technical, maybe even a little intimidating. But trust me, the idea behind it is surprisingly simple and kind of elegant. Let's break it down. So at its heart, an orthographic projection is just a technical drawing. You take different views of an object and you project them onto these things called reference planes. The two key words to hang on to here are projection and perpendicular. It basically just means we're capturing the object from very specific, straight-on viewpoints. And the name itself pretty much tells you everything. The word ortho comes from Greek, and it means straight, or in our case, a 90-degree right angle. And graphic? Well, that just means drawing or picture. So orthographic projection literally just means a right-angle drawing. See? Not so scary after all. So here's the core idea. I want you to imagine you're shining a light, but it's infinitely far away, so all the light rays are perfectly parallel. The shadow that your object casts onto a screen behind it, what we call a plane of projection, that shadow is a perfect 2D view with zero distortion. That shadow is the projection. Okay, so one perfect shadow is great, but that only shows us one side. How do we capture the entire 3D object? Well, it's simple. We just take 3 of these perfect shadows from 3 different sides. And the easiest way to picture this is to imagine the object is floating inside a clear glass box. We capture the object using 3 standard views. First, there's the front view, which gets projected onto the plane behind the object. Then we have the top view, which is projected onto the plane below it. And finally, the side view, which is projected onto a plane right beside it. Each of these planes has a technical name, but we'll get to those as we go. All right, first up is the front view. This is sort of the main event. It's the view that shows the most important features of the object. Its projection, or shadow, lands on the back wall of our glass box, which engineers call the vertical plane, or VP. Okay, next, let's change our perspective. We're going to float up and look straight down from directly above the object. This gives us the top view, and its projection lands on the floor of our glass box. This surface is known as the horizontal plane, or HP. And to complete the picture, we look at the object from the side. This projection lands on the sidewall of the box, which is called the profile plane, or PP. So there we have it. 3 separate, totally flat 2D views that capture all the geometry of our object. But hang on, this is all still an idea happening in a 3D box, right? The real magic happens when we need to get all this information onto a single, flat blueprint. And to do that, we literally unfold the box. So let's go back to our glass box. Just imagine those 3 views are now sort of imprinted on the inside surfaces. The front view is on the back wall, the top view is on the floor, and the side view is on the right wall. Now, to get these views onto one flat surface, we just hinge the box open. So the horizontal plane, that's the floor, it rotates 90 degrees down. And at the exact same time, the profile plane, the sidewall, rotates 90 degrees out to the side. And voila! This is what you get. This is the final layout. The front view is right in the center, with the top view directly below it, and the side view directly beside it, all perfectly aligned. This standardized arrangement, right here, is the blueprint. This is that universal language of engineering we were talking about. So let's circle all the way back to our original problem. Why go through all this trouble with glass boxes and unfolding planes? Why does this specific method matter so much? Because this system is completely unambiguous. It shows the true, undistorted size and shape of every single feature, which removes all the guesswork. A machinist anywhere on Earth can look at this one drawing and know the exact information they need to build the part. It's the universal language that guarantees an idea in a designer's head becomes a perfect physical reality. So, the next time you look at any object that's been manufactured, from a tiny screw to a huge jet engine, remember that invisible blueprint that exists behind it. You now understand the language that was used to create our world. So the real question is, what will you see differently now?